Mathematicians have just discovered a new infinity, one that doesn't follow any of the rules of mathematics. It's so strange, it could change how we understand logic, numbers, even the universe itself. I know, it sounds impossible, right? Infinity's supposed to be the biggest thing that there is. How can there be more than infinite? Well, it turns out that not all infinities are the same size. Some are actually bigger than others. To make sense of them, one mathematician came up with a way to organize infinity, something called the infinity ladder. And in this episode, we're gonna climb it. Each rung reveals a new kind of endlessness, stranger and more powerful than the last. But this new infinity, it seems to live on a rung that doesn't belong, one that could bring the entire ladder crashing down. This chaos has even sparked a bit of a rebellion. Mathematicians who say that we should get rid of infinity altogether. They call themselves ultrafinitists. Their argument, that infinity isn't just confusing, it's misleading us, holding science back by letting us use quantities that could never exist in reality. And if they're right, it might mean something astonishing. That even beyond what we can see, the universe itself could be finite. I'm Abi James, and this is the strange story of how we may have finally reached the end of infinity. So, how can one infinity be bigger than another? To find out, we need to step inside one of the most interesting thought experiments in all of mathematics, Hilbert's infinite hotel. The experiment was thought up by German mathematician David Hilbert, and it goes like this. Imagine a hotel with an infinite number of rooms. Now, it's a good day for the owners. They're fully booked. There are an infinite number of guests filling the infinite number of rooms. But then, suddenly, the infinite hotel's manager, let's call him Dave, finds himself with a problem. A person shows up looking for a room. Surely, with an infinite hotel, you must have space for one more, right? Luckily, Dave has a moment of inspiration. All the rooms are full, but this is an infinite hotel, and so the usual rules don't apply. Dave asks the people in room number 1 to move to room number 2. The people in room number 2 to move to room number 3. The people in room 3 move to room 4 to room 5, so on. You get the picture. Every guest moves up a room number. It's an infinite number of room changes, but this is an infinite hotel, so it's just another normal day at the office. The effect of all of these room changes is there is now nobody in room number 1. Remember, they moved to room 2. Our traveler is in luck, there is room at the Infinite Inn. So happy days! Hotel manager Dave heads to the bar for a well-deserved cocktail when suddenly, out of the window, he spots a bus pulling up to the hotel. Unfortunately for Dave, this isn't your usual kind of bus. It's an infinite bus with an infinite number of travelers expecting an infinite number of beds to sleep in. Can it be done? Well, Dave didn't become the hotel manager of the Infinite Hotel for nothing. He has another trick up his sleeve. Now, once again, we're going to need a bit of a shuffle among the guests. This time, rather than everyone moving up one room number, everyone now moves to double whatever their room number is. So the guests in room 1 go to room 2. Room 2 goes to room 4, 3 goes to 6, 4 goes to 8, and so on. The effect of this is that all the existing guests are now in even-numbered rooms, 2, 4, 6, 8, leaving all of the odd numbers free. There are infinitely many odd numbers, so as each person steps off the infinite bus, they get assigned an odd-numbered room. Once again, the Infinite Hotel satisfies all its guests, maintaining its illustrious infinite star rating. Dave signs himself up for bottomless cocktails at the hotel bar. Now, what have these room shenanigans told us about infinity? The hotel is really just a shorthand for the counting numbers. 1, 2, 3, 4, and so on, as every room has a corresponding room number. And that's why this size infinity, represented by Hilbert's hotel, is called a countable infinity. What the Hilbert thought experiment shows is that 1 plus infinity is still infinity. You can add a person to the infinite hotel and it's still the infinite hotel with the same room numbers. Similarly, the hotel thought experiment shows that infinity plus infinity is still infinity. Adding an infinite busload of people to the hotel still left the hotel the same size. It all hints at a trick that mathematicians use to show that an infinity is actually a countable one. To do that, you simply have to show that it can be paired up with the counting numbers. Or in other words, you have to be able to fit everyone into the infinite hotel. An argument like we saw for the infinite bus can be used to show that the odd numbers are a countable infinity, for example, or the even numbers. But not all infinities are actually countable. There are those that are so large, the infinite hotel would never have enough room for them. Dave's trick simply wouldn't work. These are the uncountable infinities. Now, once you establish that one infinity can be bigger than another, suddenly a different picture starts to appear. There is a hierarchy of infinities, and this hierarchy appears to be far richer and complex than we ever thought it would be. And this strikes at the very foundations of mathematics. Mathematicians have been trying to understand infinity since the dawn of mathematics. The ancient Greek philosopher Zeno realized that for anyone who wants to finish a path, say a turtle walking down the road, they will need to first go half the distance. But before that, they will need to go half again, and before that, half again, and so on. They will need to get through an infinite amount of steps before they finish. Yet, we see people and turtles finish a route every day. It was an apparent paradox. It wasn't until thousands of years later that the solution was embedded in the very structure of mathematics itself, when Isaac Newton and Gottfried Leibniz started developing calculus. They were trying to measure how fast things change, like how quickly an apple falls or how fast a planet moves through space. And they ran into the same problem as Zeno. If a turtle has to walk an infinite number of tiny steps to reach the finish line, how can you ever measure the distance it travels? The answer, they realized, is that you don't have to count every step. You just have to watch what happens as the steps get smaller and smaller. Even if there are infinitely many, they still add up to something real. If you keep shrinking those steps towards zero, you eventually reach what's called a limit, a point where the problems of infinity seem to disappear. It's like zooming in on the turtle's path until those endless little steps blur together into one smooth motion. That simple idea, adding up an infinite number of almost nothings, unlocked a new way to describe how the world actually works. Before calculus, infinity was this terrifying, untouchable idea. After calculus, it became a tool, something we could finally use to understand motion, speed, and change. It became the foundation of physics, engineering, and even the way computers model the world. Infinity had been tamed, but not for long. Over the next 2 centuries, mathematicians began to discover that there were many different kinds of infinities. But it wasn't until Russian-born Georg Cantor began to organize things that it started to make a bit more sense. Cantor created our infinity ladder. He argued that there are countable infinities, all of which are the same size. No matter what countably infinite set you are looking at, there is always a way to match it up with the counting numbers. You can always fit a countable infinity in the infinite hotel. These became the first rung on the ladder. But then, there is another larger rung above it. This is the first of the uncountable infinities. Now, exactly what this first uncountable infinity is, it's a video in and of itself. But for now, we can think of it like the real numbers. These are all of the numbers on the numbers line. This includes the counting numbers, but also all of the negative numbers, all of the fractions, all of the weird numbers like pi or the square root of 2 that would take infinitely many numbers after the decimal point to actually write down. This set of numbers, the real numbers, is so big that it is uncountable. Mathematicians have proven that no matter how hard you try, you could never assign every real number a unique room number in Hilbert's infinite hotel. The real numbers are an uncountable infinity. So, we have a second rung to our infinity ladder, but it doesn't stop there. There's a trick for moving up the rungs called the power set jump. The power set of a set of numbers is simply all the possible ways to gather the individual elements into sets themselves. So, the set containing just the number 1 would be in there, and so too would the set containing just the number 2. But there would also be the set containing all of the even numbers, as well as the set containing all of the odd numbers. Collecting all of those combinations is called the power set. And when you do this with an infinite set, you always end up with an infinity bigger than the one you started with. In other words, you jump up a rung on the infinity ladder. It's like taking the infinity from the rung below and remixing it into every possible way. Each time you do it, the infinity you get is bigger than the one before. The ladder ultimately leads to an infinity of infinities. It's fair to say that all of this did not go down so well when Cantor first suggested it. I mean, come on, infinity is infinity. Mathematicians like Leopold Kronecker rejected Cantor's suggestions, but eventually many began to embrace it, such as David Hilbert. He argued, "No one shall expel us from the paradise Cantor created." Fast forward to today, however, and the infinity ladder looks a little different. Way up above these rungs lurks even larger infinities. Mathematicians have been trying to wrestle these into some coherent hierarchy, asking, can they even fit on the infinity ladder? In 2024, Juan Aguilera and his colleagues proposed some new, very large infinities called exacting and ultra-exacting cardinals. These sets don't appear to obey any of the rules that mathematicians have come up with. They interact very strangely with other notions of infinity. To explain exactly what these sets are is to risk getting lost in the world of advanced mathematics. But to give some context, exact cardinals can be loosely thought of as containing mathematical exact copies of their own entire structure. A bit like a hotel that contains multiple full-scale models of itself, but also contains models of the surrounding neighborhood and city. Ultra-exacting cardinals have one more rule, which says that these sets must also contain the mathematical rules of how to make them, as if the nested hotel was also decorated with blueprints of itself. These unusual properties are what cause these sets to fall off the infinity ladder as they play havoc with some of the deepest rules of mathematics. To understand why, we'll need to go back to the early 20th century when mathematicians were trying to establish a strong foundation for the field. Working with Cantor's set theory, they looked to define a basic set of rules, or axioms. These could be used to build and prove any other mathematical conjecture or theory. The most widely accepted form of this foundation today, known as Zermelo-Fraenkel set theory, included a controversial rule called the axiom of choice. That is the root of the problem. This axiom says that you can always build a new set of numbers by picking out numbers from other sets, but it doesn't tell you explicitly how to do it. Some mathematicians felt that this didn't work when considering infinite sets because it would require asserting the existence of mathematical objects without identifying what they are. However, over time they came to accept the rule, and it is now used as a key measuring stick in organizing the infinity ladder into 3 broad regions. At the bottom of the ladder, the first and smallest region, contains infinities that adhere to the set theory axioms. These are the countable infinities, as well as the next rung up studied by Cantor, the first of the uncountable infinities. At the top then, the third and largest region, has infinities so huge that all set theory axioms break down, including the axiom of choice. It's a region of chaos. Now, many infinities fit somewhere between these in the second region, and initially exacting and ultra-exacting cardinals appeared to fit there as well. But when the team actually tried to pin them down, they found that it wasn't possible. It's unclear whether they fit in at the top of this middle region, where the axioms are still compatible with all other axioms of set theory, or whether they are forming a fourth region that is kind of to the side of the chaotic region, but on top of the previous ones. The answer to where these fit has some big ramifications to the future of mathematics because of a key unsolved problem called the Hereditarily Ordinal Definable conjecture, HOD for short, which proposes that as you get to the very largest infinities, the axiom of choice starts to make sense instead of leading to contradictions. This would suggest that mathematics becomes more ordered at the largest scales. It is a battle between order and chaos. If these exacting cardinals are accepted by the wider mathematical community, which isn't necessarily certain given their existence straddles the borders of maths and philosophy, but if they are, then it strongly suggests that the HOD conjecture is false, and therefore, chaos rules. And you'd think those would be the two options, right? But no. In the world of infinite mathematics, there's always another side. And this time, there is a breakaway movement. These anti-infinity rebels argue that we've got the whole thing wrong. We should just do away with the concept of infinity altogether and bring mathematics back down to earth. Meet the ultrafinitists. Their arguments are simple enough. Huge numbers and infinity are undermining the foundations of science, from logic to cosmology. We need to do away with them altogether and create a solid foundation for all mathematics without them. This opinion has grown from a small fringe group to one that is increasingly popular. In April 2025, one of its main proponents, Doron Zeilberger, spoke at an ultrafinitist conference at Columbia University in New York, packing a room with a very finite number of researchers from across the mathematical spectrum, hoping to draw a line in the sand. Zeilberger was not messing around here. Halfway through the conference, he said, "Infinity may or may not exist. God may or may not exist. But there is no need for either in mathematics." The ultrafinitist movement started in the 1960s with Alexander Essenin-Volpin, a Russian mathematician and poet, as well as a strong voice for human rights in the Soviet Union. Essenin-Volpin was looking at a problem related to a widely accepted foundation of mathematics known as Zermelo-Fraenkel set theory. We'll call it ZF theory. The thing with ZF theory is that it's extremely powerful for proving mathematical theorems, except, well, one very crucial one. You can't use the axioms of ZF theory to prove that ZF theory itself is consistent. Consistent is math speak for a system with no contradictions, which of course are bad. Essenin-Volpin outlined a program for proving the consistency of part of ZF theory. Though it wouldn't shore up everything, this program stood a chance at least of solidifying the foundations of mathematics, just as long as mathematicians were willing to do one thing. You guessed it. Abandon infinity. Essenin-Volpin never completed his program, but he lit an ultrafinitist torch that other mathematicians then picked up. In 1971, Rohit Parekh showed that the idea of a small number, though hard to define precisely, can be useful. He developed a mathematical theory where all numbers were kept smaller than a certain largest number, such as 2 tetrated to 1,000, which is equal to 2 raised to the power of 2 raised to the power of 2 1,000 times. This is far larger than the 10 to the 80 atoms in the universe. But it is still a finite upper limit. By requiring that proofs are kept below this limit, Parik showed that his mathematical framework could remain internally consistent. But beyond squabbles between mathematicians and philosophers, what does this all mean? If the ultrafinitist project succeeds in removing infinity from our mathematical toolbox, we may then have to grapple with the possibility that the universe, even beyond the bounds of what's observable, may actually be finite. Physicists would be forced to rewrite their theories using discrete, definite mathematical tools, and do away with many of the tricks that ensure modern physics works. How could the laws of physics possibly allow that? Currently, they don't. But some physicists, like Sean Carroll, have suggested incorporating finiteness through quantum mechanics, or theory of how matter at the smallest scales behaves. While the universe would still be infinite in space, the amount of different quantum states that matter could have would be finite, which would create a universe that must eventually revisit previous states. The number of possible states is still enormous, but it is an actual number, and that could pop out of our efforts to unite gravity and quantum mechanics, one of the grandest challenges in physics. Grappling with infinity, it's not unfamiliar to physicists. In fact, one of the biggest breakthroughs in constructing the standard model, or best model of how particles and forces of the universe work, involves getting useful predictions out of equations that initially give infinite results. So not all physicists are so comfortable with rejecting infinity, and they say that it would need to come out of some new theory of physics rather than just rejecting it out of principle. But mathematics, that's built on these foundations. So if there turns out to be a crack in its framework, then someone needs to know how to fix it. Could the ultrafinitists be the ones to save the day? You should keep exploring the edge of mathematics with us by listening to this podcast episode where we uncover the mysteries of busy beaver numbers. Now, they may sound cute, but they are far more complicated than they seem.